Today, another MIT integration bee. Okay guys, so today I'm gonna be integrating another lovely integral from the MIT integration bee, this time from 2018. Let's roll. So we're supposed to evaluate the integral, or rather just find the antiderivative of this infinite root tower. Hell. That's gonna be the square root of x multiplied by the cube root of x multiplied by the fourth root of x, and so on. We're just going to do this stuff infinitely long. Oh yeah. Well, first of all, I have no idea how this stuff will behave, and I have no idea how to solve it, so let's maybe first of all try and just work out, let's say, a little bit easier cases. So maybe the cases when this tower of roots is not infinite, at least. So as first of all, we'll cover the case of just the square root of x itself. Well, this is gonna be pretty easy, I think. Just gonna be just the integral of x to the power of a half dx. The antiderivative of this thing is gonna be just x to the power of 3 over 2 divided by divided by 3 over 2, and then plus a constant, because you never can forget the constant. It's once again to you engineers. Yeah, so now for the second case, let's maybe now take into consideration the second root, so the cube root of x. After that, there's gonna be the integral of the square root of x multiplied by the cube root of x right over there. So that's the same thing as just, well, separate those integrals together, they just multiply by each other. So we'll have x to the power of 1 over 2 multiplied x to the power of 1 over 2 times 1 over 3 dx. Okay, so, well, this is just gonna be, oh man, it's gonna be a 6 plus 3 6, so it's gonna be, I think, 4 6, something like this. The integral of x to the power of 4 over 6, and this is the x that's gonna be equal to x to the power of 10 over 6 over 10 over 6 plus c. I really hope I didn't make a mistake here, but I could have, because I'm not really good at adding fractions. So what we see here is that whenever we are adding in one, we are taking into consideration one more of those beautiful roots, what we get is just, oh, maybe let's say I would like to do the fourth case. So what we get is just, is just a product of x's to the powers of 1/2, then x to the power of 1/2 times a third, and then the x to the power of 1/2 times a third times a quarter, and so on and so forth. I'm not going to be evaluating this thing. And so what we can actually see is that this entire integral is just going to be nicely equal to the integral of just x to the power of 1/2. Is going to be this x right over here, and then this x right over here is going to be risen to the power of 1/2 times a third. Then this guy is going to be risen to the power of 1/2 times a third times a quarter. We're going to be going all the way down to infinity, actually, and stuff like this. But, well, what are those exponents? I mean, those exponents right here, those a half times a third, half, third, quarter, half, third, quarter, a fifth. What is this thing? Well, this half right here is just, let's say, 1 over 2 factorial, because 2 factorial is just 2. This right here is 1 over 6, which is 1 over 3 factorial. Here we've got 1 over 4 factorial, and here we've got 1 over 5 factorial. That's interesting, because now if we just multiply all those x's together and add up those exponents, what we will get is integral of x to the power of 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, and so on and so forth. But, well, if there is one sequence you should remember from Calc 2, is this boy right there. What is this? I mean, what is this thing similar to? To the Taylor series expansion of e to the x, because e to the x was equal to, or maybe no, I will just say e to the first power is equal to 1 plus 1 over the 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on and so forth. The more of those terms we add up together, sorry for hitting the microphone guys, the more accurate the approximation is gonna be. And so, well, we have an infinite sum right over there. This thing is e. However, we are not adding this 1 and 1 over 1, so we are actually, well, deleting those. And so we'll have that this is gonna be equal to, well, this 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on is gonna be equal to e minus a 2. And so we see that this entire exponent here is gonna be equal to e minus a 2. And so this entire I wanted to say derivative. This entire integral is gonna be equal to x to the integral of the x to the power of e minus 2 dx. But well, what is e minus 2? That's just a constant, so we can just go on and use the normal exponent rule. So no integral now. It's gonna be equal to x to the power of e minus 1 all over e minus 1 plus a constant, and this is exactly the antiderivative we're looking for. So once again, what did we do in this problem? Well, we first will consider cases that are not, well, infinitely long right over here to just get the sense of what's going on under all those square roots. And then we notice that after expanding, then we made the conjecture, and then we use that conjecture to expand the entire it's not really a tower, it's rather a cave. It's the cave made by those square roots here in this integral, getting that actually what we're gonna get by multiplying out and summing up all of those exponents right there is just gonna be almost the Taylor expansion for e to the first power. That's gonna be actually the Taylor expansion for e minus 2, and so we use that fact to evaluate our integral pretty smoothly. That is gonna be just equal to e x to the power of e minus 1 all over e minus 1 plus a constant. I hope you guys enjoyed it, and see you in the next one. Bye.